Hey everybody, John Mason here. How you doing? We're in the lab. What we got here is a little kind of a bubble chamber that's going to hold an electron beam for us. There's very little air pressure in here, just a little bit of helium gas to give off light as the electron moves. And there's a little cathode ray gun here in the bottom of the chamber. And actually what I can do is turn the voltage. This thing has an accelerating voltage, and I can turn the accelerating voltage on, and we get a little electron beam that kind of ejects across the lower part of the screen here. Now, if I cover this up, just to make it dark, we have some Helmholtz coils here. These are have a radius of 14 centimeters, and the Z, or the distance from one coil to the center where the electron beam is 7 centimeters. And so this is the geometry of the Helmholtz coil. Now what I can do is I can turn, when I use this knob over here that you can't really see, I guess if I turn this. So if I basically take this knob here, this knob's a little finicky, so I'll do the best I can. But if I turn this knob, I can create amperage that will make a magnetic field that will bend this electron beam in a nice circle for me. So let me turn the, when I turn the magnetic field on, I get current going through the coils, which makes magnetic field. And so this electron beam is exposed to the roughly uniform magnetic field in the middle of the Helmholtz coil, in which case the electron beam basically undergoes the circular orbit. Now, by looking just at the accelerating voltage, the current in the field, the current in the Helmholtz coil, and the radius of this orbit, we can actually figure out since we know that these are electrons, or since I'm telling you these are electrons, we can get the charge to mass ratio measurement out of this. And so here's how it works. So here, the accelerating voltage I've got is read off on this voltmeter over here as 166 volts. All right, so that's the accelerating voltage. And the current that's going in the coils here, I'm going to use my clamp meter and basically use Ampere's law to figure out the current going in the coils. So there I have 143 amps. So it's 166 volts, 143 amps. And now the radius of the orbit, I'm going to take and measure with a ruler. So I have a little ruler here, a little clear ruler, which I'll set up here like so. And by looking here, you can basically measure the radius of the orbit, which I'll just turn to the side to do it myself. Okay, so what I'll do is turn this to the side and make the measurement. What I'm going to do is I'm going to hold my eye at a fixed length of 30 centimeters away here, like so. And I'll measure the radius of this orbit. So I set myself up like this, hold my eye at a fixed length, and I'm going from, oh, my ruler's backwards. Here we go. Okay. And the diameter of my orbit goes from about 11 centimeters to 18 and a half. So the diameter of this orbit is 7.5 centimeters. Okay. So I have 143 amps, 166 volts, and a 7.5 centimeter diameter for this orbit. And now from that information, that's a first set of data points that you can take for this experiment. And then the next set of data points, what we try to do is adjust the current a little bit, which is actually kind of the hard part to do for this knob. This knob doesn't really want to change current very much. So maybe I'll try to get one more measurement. So there's a bigger radius orbit right there. This one's being accelerated with 209 volts, okay? And the current is probably still 143, let's see. Oh, okay, I got the current now, it's 117 amps. So that's 117 amps, 209 volts. And now I'll make the measurement of the radius that's present here. Okay, so if I look at this one, this diameter goes from about 10 centimeters to 20 centimeters. So that's a 10 centimeter diameter as I measure it, as I look at the thing. Okay. Now I can try to get a smaller voltage here. Just a small little. Let's try this one. Okay, so here we go. Now I've got, whoops. My little voltmeter came out there, so let's do another measurement. Let's turn this guy back on. A nice light current there. So now, sorry, this is a little slow, but there I've got a very faint orbit now, but I've set up this one at 100 volts, and the current running through the amp meter is 106 amps. So there's 106 amps, 100 volts, and I'll measure the diameter of this one now to be 12 to 19. So that's a 7 centimeter diameter. All right, nice. And I'll do one more measurement for our fourth set of 3 measurements. And we'll try to get a high current here. Can I pump this thing up at all? There we go. Nice. Okay, so now I've got a pretty high current, which I'm going to measure as 224 amps and 247 volts are what are showing up on the voltmeter. So 247 volts. And now I'll measure the diameter of this guy, which is going to be small. So here we go. If I look at this, going about 12 to 18. So that's a 6 centimeter diameter. And so those are the different dimensions here of sort of our 3 sets of measurements, where we have voltage on the one hand, accelerating voltage, the current in the Helmholtz coils that you use to calculate the magnetic field, and then the apparent radius, the apparent diameter of this orbit. And so I can turn the B field off, I can turn the voltage down, I can turn the machine off, and those are our basic data for the E to M ratio. All right. Now, the only catch is that as you work through your experiment, there's I held my eye at a fixed length. And so what I have to do is the diameter we measured by eye here was not, I didn't put the ruler on the actual thing I was measuring. And so it's kind of like measuring the diameter of the moon with a ruler. If you measure the diameter of the moon with this ruler, it'll show up to be a few centimeters, but of course the moon is much bigger than that because it's very far away. Well, it's a similar story with the radius or apparent diameter of the electron beam. If we want to know ultimately the radius of the electron beam, then what we need to do is know the actual diameter. Now, the numbers I gave you were the apparent diameter, but those need to be scaled up because the actual diameter is bigger because it's a little further away than where we were measuring. And so what you do is you scale up by a factor that is 30 centimeters versus a ratio that's 30 plus the 7 centimeters to get to the middle of the apparatus. And so take the number 37 over 30 and scale up the diameters that I was measuring by those amounts so they're bigger, and then divide by 2 to get the radius of the beam. And then you can use that with your measurements. The current that I called out basically goes into the equation for the Helmholtz coil B field to calculate the magnetic field. and the voltage is the voltage. And then you can calculate the charge to mass ratio of the electron by taking 2 times the voltage divided by BR squared. And you can do a little algebra exercise to prove that that is the charge to mass ratio of the electron. And that'll give you 4 different measurements for the charge to mass ratio of the electron. You can take the average to get your average measurement. Then you can take the accepted value for the charge of the electron, 1.6 times 10 to the minus 19 coulombs, and the mass of the electron, 9.11 times 10 to the minus 31 kilograms, get the actual ratio of those two numbers to get 1.75 times 10 to the 11. And then you can compare your experimental value, your average, to that amount as a percent difference. Okay, so that is a lightning charge to mass ratio lab. Thanks, everybody.